So in this video we're going to talk about heat and entropy. This should be revision for most of you, or all of you, but we're going to go through a summary of what these concepts mean, and just to remind you of different things. Okay, so if you look at the textbook by one, you will find enormous numbers of partial derivatives. Okay, as typical of thermodynamics textbooks, they're full of first derivatives of state variables and first derivatives of the state functions and second derivatives and all kind of Maxwell relations relating those. We're not going to cover those in this course and not going to use them either. When it boils down to things, what you need for thermodynamics are the laws of thermodynamics. Okay, everything is derivable from those laws. Okay, so so we're going to avoid all these horrible partial derivatives, which nobody loves, just like the young girl in Charles Blackman's painting. Okay, so the natural variables for state functions are usually things like P, V, and T, since you can measure those. I mean, sometimes you can measure the magnetization, for instance, in a magnet. We can use other variables, and for instance, you can express the internal energy U in terms of the entropy, volume, and temperature, but most people don't have access to an entropy gauge, and so therefore that's not fantastically useful in real situations. It can be useful in theoretical situations, but that's where it ends. Okay, so as an aside, using the first law, du equals dq equals du plus pdv, where P here would be the pressure in the container, and defining the enthalpy as H equals U plus PV. We'll get on to defining entropys later on in the next lecture set. We can get the heat capacities in terms of U and H. So CV is normally dQ dt at constant volume. But it also turns out to be du dt at constant volume as well. Okay, and similarly Cp is dH dt at constant pressure. So sometimes those two relations are useful. Right, so let's go to a particular example, which is the free expansion of a gas. Basically, you have a gas which is confined in one half of the container at some temperature T1. And then you just remove the stopper here between the walls and the gas expands into the other half of the container. This is called the Joule experiment because it was first done by Joule. It's not the same as the Joule-Thomson effect, which some of you might have met as well. Very much different. Okay, so we look at gas expands into a vacuum and the whole system here is thermally isolated. When Joule did this experiment, he found that the temperature of the system was unchanged, and therefore this implies that dq should be equal to 0. Okay, because dq is Cv dt. Okay, Joule also knew the work done by the gas was 0, dW equals 0, because the gas expands into a vacuum. There's no opposing pressure here. The gas just comes through. It's not opposed, so the work done must essentially be 0. And therefore, from the first law, because du is equal to dq minus the work done by the gas, it must be true that du is equal to 0. So Joule said, well, in this particular experiment, the change in internal energy of the gas is 0. Okay, so what does that tell us? Well, if we choose v and t as our independent variables, since u is a function of v and t, it must be true that u v1 comma t is equal to u v2 comma t, because temperature is constant here. Okay, when you do the experiment, the temperature is constant. Okay, so this means, because we have also have PV equals nkt in RT, that u is independent of pressure for the system, so therefore u depends only on the temperature. Okay, for a gas, at least an ideal gas, u depends only on temperature. Okay, and this tells us that Cv is du dt, which is du dt without the derivatives. Okay, so u depends only on temperature for an ideal gas, the internal energy. So experimentally, what's found is that CV is a constant, more or less, okay? So that for an ideal gas, U is equal to CV times the temperature, okay? Now, real gases, of course, are a little bit more complicated, okay? So real gases have intermolecular forces. You've probably seen this kind of picture before. You have two gas molecules here, which are represented by spheres. There's some distance between them, and the energy of the system for these two molecules depends upon this distance r. So this is r here, this is u, and the typical way it depends is often modeled by this Lennon-Jones interaction potential, which goes as at very, very, very large r, it goes as 1/6, it's attractive, and then at very small r, it goes as 1/12, and it's repulsive. And in the middle, of course, there's some equilibrium position, but of course the system doesn't sit in the equilibrium position because it's got thermal energy, and so it's always sort of sampling all the way around here somewhere. Okay, it's sort of often sampling up here. Okay, so you've got real gases have these intermolecular forces present. Long range, they're attractive. Short range, they're repulsive. Okay, so the fact that they're at long range, they're attractive, means that when a gas expands, the potential energy goes up. Okay, because if I'm located here as my typical distance, let's erase this stuff. Okay, if my typical distance is, say, here, this is where I am before I expand, and then I start expanding, let's expand, so the distance must increase, the energy has gone up, so the total energy, the internal energy has gone up, the total energy must be the same, so the kinetic energy of the molecules decreases. Okay, so U potential has gone up in this case, U total must be the same, because we're not doing any work or anything, so therefore the kinetic energy must go down, and basically the system cools. Okay, so most real gases cool upon expansion. However, the opposite will be true if you have a very, very dense gas. You have a very, very dense gas. Suppose I'm really up here, I'm really dense. Okay, distance between particles is very small. When I expand, I go this way, distance increases, my potential energy goes down, the total energy must remain the same, so UP plus U kinetic must be a constant. Okay, this has gone down, so this must go up, and in fact the gas heats up upon expansion. That's for a real gas. All right, so if you look at the Joule experiment, the Joule expansion, you will see slight corrections to this kind of behaviour where you say, well, the gas doesn't change in temperature. It's not quite true. Okay, and the fact that it does change with temperature tells you something about molecular forces. It tells you how non-ideal the system is, actually. Okay, so just to remind you of the adiabatic expansion of a gas. Often things are adiabatic, and it's a very good model for certain things, in particular for certain parts of the car engine cycle. So here's the Italian actress Sophie Loren with her Mercedes Gullwing doing our calculation for us. When we get adiabatic expansion, of course, that means dQ is 0. Adiabatic means no heat flow into or out of our system. dQ is 0. Okay, it's the same thing. We haven't really introduced entropy, but when we do, it means no entropy change as well. So ds is 0, and it means well insulated, or it can mean fast. Fast just means, like in a car engine, for instance, it's fast. Heat doesn't have time to flow. So it means all of these things normally. But adiabatic, when you think of adiabatic, you should think of that and that. Okay. Right, now, of course, the other application of that is in the theory of sound, where you have the compressions and rarefactions in a sound wave are adiabatic. And famously, of course, Newton got his speed of sound wrong because he assumed the compressions and rarefactions were isothermal. Okay, so du is equal to 0 means, dq is equal to 0 means du equals to w, which is minus pdv for this system. So we're going to compress a gas or expand a gas, okay, under adiabatic conditions. Now, when our gas, here's our gas, and expand it, because we have du equals cv dt. Now, remember, this is always the formula for du for a gas. it's always equal to CV times dt, irrespective of whether you're doing a constant pressure or constant volume. du, not dq, but du is always equal to that. Okay, so we can write down the first law as CV dt plus PdV equals 0. We also have PV equals nkt. Okay, so we can eliminate t. Let's eliminate t. And then we have from this, we have just differentiating this, we have nkb dt equals pdv plus vdb. So we'll take that and differentiate it there. Put that up into there, this thing up into there, and we get this. Okay, gamma dv on v plus dp on p equals 0, where gamma equals cp on cv, yeah, there should be a correction there, is the ratio of the specific heats. Okay, and normally it's about 1.4 for most gas systems. Okay, so we have this equation for adiabatic expansion or compression, and if we integrate that, we just integrate it, you know, this becomes gamma log v plus log p equals a constant. We get PV, the gamma, as a constant. And because PV is nkBT, we can also write that as TV, the gamma minus 1, as a constant. This is also an alternative version. I tend to remember this one. Okay. Now, what does that tell us? Well, that tells us that when a system is compressed adiabatically, it gets hot. Okay, and it tells us, in fact, how hot it gets. And this is the basis for fuel ignition in a diesel engine. In a diesel engine, you don't have spark plugs. You just compress the gas, the air-fuel mixture. And when you compress it, like, where's the compression stroke here? The compression stroke is going to be pushing up. So this is compression. It's going down. It's got air coming in. That's an intake stroke. Here's the compression stroke here. It's being compressed, and when it's compressed, it will ignite. Okay, because the volume is decreased, and then you will get some you'll get ignition and the fuel burns. Okay, so that's the basis for the diesel engine. Okay, now next thing we're going to do here is what? The Carnot cycle. All right, so if we have a cyclic process, by definition, if it's cyclic, the final and initial states are the same. Okay, this is in sort of models of engines where you take a system and you take the same amount of stuff. You don't allow. It's not like a car engine where you're allowing, exhaust gases to get out of the cylinders and all that kind of stuff. In a cyclic engine, we basically keep the working material contained in the system and don't allow it to leave. Okay, so if it's cyclic, the final initial states are the same. By definition, if it's cyclic, it's gone round a cycle and it's back to where it was. And therefore, the state functions are the same. So in particular, the internal energy U and the entropy S must be unchanged when you go round a cycle. As I said before, in real internal combustion engines, they're not cyclic because they ingest material and spit it out. And so the working fluid is constantly changing. However, you can approximate them by engines which are cyclic. Okay. Now, the Carnot cycle, which you've all seen before, is not a practical way of generating work, normally generating power, but it's an interesting theoretical cycle. And so a working substance is taken around a loop in 4 steps. Okay, we've got 2 isotherms. So we've got isothermal expansion, isothermal contraction. This is a PV diagram, indicator diagram. And we've got 2 adiabatics, okay? Adiabatic compression and adiabatic expansion. Okay, so we got 2 different adiabats and 2 different isotherms here. Okay, so in fact, which ones? Yeah, okay, all right. So in the Carnot cycle, we have a cycle, so du is equal to 0, and we must have dw equals dq around our cycle, because if we're going around a cycle, you must have du equals dq minus dw, and that's 0, so therefore the du must equal to w. The amount of work done is equal to the amount of heat absorbed. Okay. In the Carnot cycle, no heat is input or output during the adiabats by definition. Okay, so if you go to the adiabatic bits, which are here, there's no heat input or output. Okay, all right. And an amount of heat Q2 is added in the hot isotherm at temperature T2, and an amount of heat Q1 is rejected in the cold isotherm at temperature T1. So heat added, heat rejected. The work done, of course, is just the difference between the heats, because du must be equal to 0. And the efficiency is always defined as the work done divided by the heat added. This is the heat added, not the total heat, because if you did W divided by Q2 minus Q1, you just could always get 1. Okay, so it's the work done divided by the heat you've added. And that's equal to 1 minus Q1 on Q2 because of this result here. Okay, so that's how we define efficiency for an engine. Right, so there you've met that before. That's the Carnot cycle. Right, so let's go to the second law of thermodynamics. Okay, that says that there does not exist a thermodynamic transformation whose sole effect is to deliver heat from a reservoir of lower temperature to a reservoir of higher temperature. So that's one way of saying it. Or you can say there does not exist a thermodynamic transformation whose sole effect is to extract heat from a reservoir and convert it entirely into work. This is still law of thermodynamics. It's not as useful as the first law, but it does tell us something interesting. Okay, basically it tells us the heat doesn't flow uphill. Okay. So how do we define temperature? Well, the textbook gives a way of doing this. I'm not going to go into it very much because I'm assuming you already know about temperature rather than we having to define it. But the absolute temperature of two reservoirs in the Carnot cycle is defined by this. Okay, ratio of temperature T1 to T2 is 1 minus Q1 on Q2. So you can measure the heat input for those two reservoirs, and that defines what the temperature is. And that turns out to be 1 minus the efficiency. Okay. And Huang gives a proof that no engine can be more efficient than a Carnot engine. I think the Stirling cycle has the same efficiency. But if operating within the same temperature limit. So we won't go into that proof, but we're not still going to do that. Okay. So now what we've seen before is dQ is not an exact differential. That's the heat added. Remember, Q is not a state function, so how you go between two endpoints depends, the amount of heat you have to add to get between them depends on how you're doing it. Okay, all over the place, okay? So that means that the Q is not an exact differential. It actually depends on how you're going between these 2 points. Okay, but we can make an exact differential out of it if we divide by T. Okay, so we take dQ on T, and that is an exact differential, and that is a state function, same thing. Okay, and that we call the entropy change. Okay, entropy is a state function, and entropy differences do not depend on the path. Really important. They don't depend on how you get there. They're like the internal energy. It doesn't depend on how you get there, okay? And that's really one of the crucial things that thermodynamics taught us, and it's one of the things which people have tremendous trouble with understanding what entropy is and how to use it, and it's mysterious, okay? So let's state Clausius' theorem. So in Clausius' theorem, any cyclic process, the integral of dQ on T is never positive. So that's Clausius' theorem. Okay, the dQ on T is never positive. Okay, now note here we're not talking about equilibrium processes. Okay, this is any cyclic process. Okay, now one gives a proof of this which we will not. You can read it by yourself. We're going to skip it. Okay, so we're just going to assume we know Clausius' theorem. So stated again, we have a cyclic process dQ on T is less than or equal to 0. Okay. If this process is reversible, we can run in reverse and the signs of the Qi are reversed, so we get this, which implies for a reversible cycle that must be true. If that's true and that's true, then this must be true. Okay, dQ on T is equal to 0 for a reversible cycle. Okay, now, and remember we've called this thing entropy, entropy change. Okay, so if we have a reversible cycle engine, then we get dQ on T, integral that is equal to 0. And this gives us an extra equation which goes beyond conservation of energy. Remember the first law gave the conservation of energy. This is something extra. You can't get that from conservation of energy. If you can get that from conservation of energy, you could get rid of the second law of thermodynamics, and you can't. Okay, so this gives us something extra, something that's a bit weird. Okay, most people have no trouble understanding conservation of energy. It's been with you as physics students for many years now, but Clausius' theorem is a bit weirder, a bit stranger. And the fact that we have a reversible path state function like this, to q on t equals 0, allows us to define the entropy difference between any two states, B and A, via this. Okay, so if we know for a reversible path you get that, it must be true that if I take a state B and a state A, that I can define the entropy difference between B and A being equal to that for any reversible path. So therefore, this thing S is a state function just like altitude or gravitational potential energy. Potential is in mechanics. Okay, your altitude does not depend on how you got there. Your altitude only depends on where you are. Okay, your gravitational potential energy doesn't depend on how you got there, only where you are. Okay, it does not matter how you got there. And if you go in a complete cycle, of course, you're back where you started from. And so in a complete cycle, the entropy change must be 0. Okay, so this definition of entropy is a direct consequence of Clausius' theorem, and the fact that entropy is a state function is a direct consequence of Clausius' theorem for a reversible path. Okay. All right. So here's a warning. Okay. S is a state function. Okay. Absolutely true. But to get the entropy difference, which is this calculation here, you must use a reversible path. Okay. If you use a path which is not reversible, then what you find is this thing is actually greater than or equal to SB minus SA, and it's not so useful. Okay, so we will go into calculating entropies at some stage, and when we do that, you have to use a reversible path to calculate the entropy. Otherwise, this equation is not true. Okay, it has to be used for a reversible path, even though when you calculate the entropy change itself does not depend on what path you take. Okay, it could be reversible, irreversible. This left-hand side doesn't depend on what path you take, but setting that equal sign there, setting those two things equals, implies that you have taken a reversible path on the right-hand side. Otherwise, that equation goes out the door. You can't use it. Okay, so let's calculate the entropy for an ideal gas, the temperature dependence of it. Okay, so start with anyway. So this should be SB minus SA, not SB equals SA. I'm going to use this equation here, which we got before. Okay, so S is a state function, so being expressed as a function of any pair of P, V, and T, and N if you wanted to keep N in there. Let's choose V and T as our variables, and we want to calculate the entropy of this state here. Okay, so how do we do that? We can say, we can calculate it by going from path 1. And if we go from path 1, path 1 is a fixed volume path. The volume is fixed, going up there. And we're going to go from T0, which is maybe there, and at fixed volume. So SVT is SVT0 plus dq on T. Now the Q is, of course, we're doing fixed volume, so it's CV dt. And we're going from T0 to T. And so we have the entropy of an ideal gas, if we know certain things, is going to be SVT naught, which we don't know yet, plus CV log T on T naught. Okay, that's the temperature dependence. Now we can get the volume dependence. And the volume dependence, we're going to choose a path to get to here, which is isothermal, but where the volume, of course, can change. Okay. Isothermal for any ideal gas applies to U as 0, because remember, U for an ideal gas is only a function of T. So if the temperature is not changing, U must be a constant. So U must be equal to 0. If the U is equal to 0, the first law gives us dQ equals dW, which is PdV, and PdV is going to be NKBT dV on V, because that's from the ideal gas law, PV equals NKT. And therefore, we can write down how the entropy change, what the entropy change is. It's SV naught T. Okay, we're starting off here somewhere, V naught at some temperature, and we end up at the same temperature, of course, because it's isothermal. And that is given by, we're going to use this equation again, dq on T. Remember, dq is nkbt dv on V, so this is our entropy change here, and we end up with SV naught T plus nkb log V on V naught. Okay, so I suggest you go back through those two slides and look again and see if you can do that yourself. So we have the following formulas. We know the entropy is a function of volume and temperature, looks like that, and we also know it looks like that, and they must be the same. So the only way they can be the same, if you think about it, is if the entropy as a function of volume and temperature looks like a constant, plus nkbt log V plus CV log T. And if you have an ideal gas, which is monatomic, we know that CV is nkb times 302, and therefore this is our formula for the entropy of an ideal gas. And it all looks fine. However, there is a slight problem. Our formula, which we derived here, is not extensive, i.e. the entropy of particles should be a function of the density, but in our case it's just a function of the volume. Okay. To get the correct formula, you have to go to quantum mechanics, which we're not going to do yet. And the correct formula is this one, which looks more or less similar, but it's got some changes. Okay. And here lambda is the thermal wavelength, which we will meet many times later on. And you can see it's got quantum mechanics in it because there's a H bar there. Okay. And M is the mass of our atom. So it has similar dependence on volume and number of particles and things, but it's a little bit different. So that's called the Sackur-Tetrode equation for the entropy, after the people Otto Sackur and Hugo Tetrode, who discovered it independently in 1912, a long time ago, the very early stages of quantum mechanics, in fact, and in fact at a stage when, of course, statistical mechanics was reasonably well developed, but still not fantastically well developed. And Tetrode is amazing because he was 17 when he did his work. So most people, 17 these days, are still regarded as children, but that's because there's been a gradual infantilization of things, and adulthood has been gradually delayed. So whereas in 1912 you were 17, you were basically an adult. And so Mr. Tetrode, derived this thing when he was only 17. Unfortunately, both Sackur and Tetrode died at the age of 34. Okay, independently again. So they derived the equation independently and died independently. Just happened to be the same age. Sackur died by mixing two chemicals. Chemistry is always bad for you. You should realise that. And Tetrode died from tuberculosis, which these days you can cure easily with antibiotics, but in the early part of this century, early part of last century, you certainly couldn't. Before the Second World War, in fact, you couldn't cure it. It was often a death sentence. So let's finish up by looking at a problem. Okay, a real problem. So we have a cylinder of cross-sectional area A, divided into two chambers, 1 and 2. Okay, and it's got a frictionless piston. I wish they existed in real life, but they don't. But anyway, we've got a frictionless piston. It's got the walls of the chambers are perfect heat insulated, so there's no heat coming out of here. The chambers have equal lengths L. Both chambers are filled with 1 mole of helium gas with initial pressure at 2 P0 on that side and P0 on that side. The piston then is allowed to slide freely, slowly presumably, but freely, whereupon the gas in chamber 1 pushes the piston distance A to equalise the pressure P. And we're asked to find the distance the piston travels. If W is the work done by the gas in chamber 1, what are the final temperatures T1, T2 in the two chambers? What's the final pressure? And find the work done. Okay, so let's do it. Everything is insulated. There is no heat flow, so that means it's adiabatic. We're going to make L left and R right. This is left, this is right. Initial pressure on the right is P0, on the left it's 2 P0. Both have volume V0, and after the piston moves, so both have volume V0 initially, after it moves, they have volume V left and V right. And we can use, remember this P, V to the gamma is a constant. We can use those equations here. And so you must have this being true, and that being true. and the pressures must be equal at the end, otherwise the piston would move, and therefore P left equals P right. And we know what the ratio of the volumes is because we know what these lengths are in terms of A. And therefore we're going to find out how big A is, and the answer is that there. So that's the distance that the piston's moved. The work done is given by the pressure times the area times the distance moved, and you just integrate the pressures as you're moving, and when you calculate that, you'll find the work done is that integral there, which you can do yourself. Okay, and that is the end of this video.